Okay, now we start the more exciting part, quantization-aware training. As embedded deep learning engineers or scientists, at some point in your career, you will have to do this quantization-aware training because, okay, training is fantastic. You do training. Some guys do training if you know how to do training, and they are using fantastic precision like double or float, but actually this is not the right way to do it when you're working with embedded systems. So, in order to minimize the loss of accuracy for aggressive quantization, many methods that target, for example, 4-bit integer precision or lower in some cases, for integer 8 as well, however for lower, involve training the model in a way that considers quantization. So you train your network with a strategy which considers that you can only use a limited precision. So when you update your weights during your training, you are keeping in mind that you have a quantization precision, because usually the default training methods do not do this. So this means training with quantization of weights and actuations. The act of training with quantization of weights and actuations, the act of training with quantization is baked. It is embedded into the training procedure. Okay, I've been talking about this training. What is training? Well, if you're asking what is training, and if you've taken the previous semester's course, I'll really feel bad because you have to know this. But if you don't know that, if you don't know what is training, most probably you haven't taken this course yet, or you haven't taken a deep learning course which covers training. I strongly recommend just getting on some training stuff, guys. For example, there's a nice YouTube tutorial here. Let's get to that. It explains what is backpropagation.
We live in strange times.
Sorry. So you just watch it. It's a very nice tutorial on what is backpropagation.
The core algorithm behind
how it works. But before that, you could check our slides here. Week 3 and week 4 actually explain the training in the previous semester's lecture. So I strongly recommend you cover these, guys. Otherwise, it's going to be lacking something. Okay then, imagine. However, before we get to more details about quantization-aware training, and in the following weeks, I'm going to cover those concepts as well. Before that, I'm going to make a small introduction so that it will help you with your own studies. And for those who have taken the previous semester's course, Convolutional Neural Networks EE545, this should be a reminder. Okay, what was backpropagation? Guys, do you remember the time I told you when you think about a neural network, whether it's convolutional or fully connected, you can just represent it as a computational graph. There are inputs, there are layers, and each layer does some operation. So there are inputs, this is an operation, but there are layers. So it's a cascaded layer structure. Inputs, some layers, some values, actuations, another operation, which is a layer actually, another operation. What you do is you pass information forward. This is called the inference. So there's input, you get the output. And these operations have some parameters. They are called the weights. Those weights have already been found for you during something called training. But how does this training work? Actually, this training works with a simple principle. You make a forward pass, then you have a result. You know that if this result is true or not, because you have a ground truth. You have fed a cat image, and there's a guy who is telling this is a cat image or not. If you could find this as a cat image, this guy will tell you that you are doing right. If not, it will tell you you are doing wrong. This is called the loss. And you minimize that loss using an optimization formula. And by judging the amount of loss, you create something called a gradient, and you pass that gradient backwards. That's called the backpropagation. So you pass that gradient backwards and backwards and backwards. While you are passing that gradient backwards, you update your weights. And you do this operation iteratively thousands of times. Forward pass, find the loss, just iterate back the loss gradient, update your weights, try it again, just iterate back, forward again, backpropagation. Forward pass, backpropagation. This is called an iteration. You do these iterations thousands, millions of times. And after some point, you train your networks and your weights are settled. This is called backpropagation, and the way you feed the gradient is called gradient descent. I strongly recommend you cover those videos and get a better understanding of it. But I'm going to try to give you the mathematical operations we do when we are dealing with backpropagation. So at each layer we have a layered structure. During forward run, we will feed some inputs. The green arrows are the forward run. We feed green values. We have a layer here. It makes an operation. And we have the actuations output. During backpropagation, a gradient will come from the other side. Due to the gradient here, we will update the parameters inside, and we will feed the gradient to the preceding layers, the layers before them. And this is the operation, and this continues on and on and again. This is called backpropagation. Okay, we do the backpropagation in vectorized operations. So you have an output of this value, you just feed it. This is a ReLU layer, and you just feed it back. That's how you do it. As I told you, just cover the slides and try to get a more idea. And how you do it is, at each step of the backpropagation, you are getting the loss error, the gradient of the error, with respect to the weights at that layer. So you have some weights at that layer. You calculate the partial derivative of the error according to those weights, which is called the derivative of the loss according to the weights, and you update them with a learning rate. So this is the derivative of the error with respect to the weights, the old weights, and you update the weights. This is the new weights. So you do this operation millions of times. They are called iterations. So there's another view of it taken from the Matlab toolbox. So training targets, you calculate the loss. So what you do is, you have training data, you input it, you have some random values for the weights, you calculate the forward pass, you calculate the loss, you find the gradients, you make the backward pass. And you do this on and on and on and on and again. Okay, that was an introduction for you to understand it better when you do your own studies. So what is the pseudocode? What we do is, we initialize the weights while a stop criterion is false. So during training, we do this iteration millions of times. For example, while you do it a millions of times. We do a forward pass. We calculate the loss. Then, for each layer, we get the derivative of the loss with respect to the weights. We calculate it. We multiply it with a learning rate. And we update the weights. And we do this again, forward pass, forward pass. So, what I explained in the slides here, we have the pseudocode here like this. So how it's going to be quantization aware? How are you going to do it? Very simply put, this pseudocode will change like this. The blue parts will be added. First, you quantize your weights. You do the forward pass using the quantized weights. So you obtain some activation values, and you quantize the activation values as well. You update your weights, and you quantize the weights as well. And you do these, you quantize weights here, and you do this at each iteration with these additional steps, quantization steps. In the end, your training procedure becomes quantization aware. And can you do this on your own? Actually, you can. Because in Matlab's training toolbox, Matlab's deep learning toolbox, there is no quantization aware functions yet. I mean, in future, maybe in future versions of Matlab deep learning toolbox, we can have them, and I'm sure that we are going to have them, because for Caffe and other Python libraries, we are seeing that those things happening. But Matlab is a bit following their steps. They are following it from a couple years from behind. But you can do it yourself. Actually, the ones who have taken the previous semester's course, we have used this function, train_network.m. So this function. You can change that function. Actually, you can change that function. You can get in that function and change it and create a new function. Inside that function, there's another function called train_m. You change it. Inside that function, there's another function called activations. You change it. And some of the functions, you just trace the functions that the toolbox uses. You duplicate them. You give them new names, and you could create your own toolbox, and which will be quantization aware. And actually, this is a very nice project title for this year's course. And actually, I'm about to assign this project title to one of you. Actually, she knows herself, but this is a very nice title. And if anybody wants to join, we could make a teamwork, which one part will be transforming some of the M files, whereas the other person is going to do. So we could share it because it's a big load. But this is a very nice title, and I'm hoping that some of you will be interested in doing this. Okay, this is quantization-aware training, and in the following weeks we're going to cover these concepts, guys. I think it's enough for this week. Please check the slides once again. Go over the papers. If I know you cannot read all of them, but if there are some papers that just attracts your attention, just read them. Come ask me questions, send me questions. I'm going to prepare question and answer video clips so that I could answer your questions here. And in the following weeks, we'll attempt to do these, guys. We'll attempt to do these things and see if it's working, if we could do quantization-aware training, and we'll continue. Thank you very much. See you next week in the next video.